friends, as you are aware, in previous class we were discussing about probability distributions and we have seen two discrete distributions. The first one was binomial distribution, and we have seen that in binomial distribution the probability of outcome remains fixed and you will always have only two outputs. For example, when you toss a fair coin, you will always have either heads or tails, right. So, the outcome would always be only two, right. For example, failure or success, whether it will rain or it will not rain and so on, right. So, the you will have only two outcomes and probability also remains fixed. We have also seen Poisson distribution, which is again a discrete distribution, and Poisson distribution is a distribution wherein we try to find out probability of rare events. For example, let us say what is the probability that there will be an accident in, let us say, in any atomic energy plant. So, it is a rare event. So, you can find out probability of such a rare event using Poisson distribution. Poisson distribution also helps in knowing the probability of accidents happening at an intersection, what is the probability of a vehicle coming at a toll booth, what is the probability of phone calls going from a switching board system. So, all these processes can be defined by Poisson distribution. And we have seen Poisson probability function, which is f of x is equal to is the mean to the power x e to the power mu and x, right. So, we know that this is mean number of occurrences in a given interval and e is equal to 2.71828. So, let us work out couple of examples related to Poisson distribution. Let us take this example of Mercy Hospital. So, we know that patients arrive at the emergency room of Mercy Hospital at the average rate of 6 per hour on weekend evenings. So, we know mu, right, just 6 per hour, right. What is the probability of 4 arrivals in 30 minutes on weekends evening? Now, this is what we have to calculate. Now, if you look at this arrival rate is given in terms of per hour, while we have to find out probability of 4 arrivals in 30 minutes. So, we need to convert this arrival in terms of 6 or how many arrivals per 30 minutes, then you can apply the probability function formula. So, let us look at this. So, this is 6 per hour, in other words 3 in 30 minutes time, is not it. So, this is your mean and x is what is the probability that the at the weekend you will have 4 patients. Okay. So, this is f of 4, it is mean to the power x, right. What is our formula? It is mu to the power x e to the power minus mu, right. So, e is 2.71, mu is 3, right, divided by factorial x, right. So, this is x. So, you will get answer as 0.16. So, what was the question? The question was what is the probability of having 4 patients arriving in 30 minutes time on weekend evening. So, that probability is approximately 17%. Okay. Now, the same answer can be obtained using Poisson distribution tables. So, if you look at any book of statistics, you will get Poisson distribution tables similar to binomial distribution tables. So, here our question is what is the probability of 4 patients arriving during weekend, given that mean was 3, right. So, these are x values and these are mean values, right. So, for mean is equal to 3, x is equal to 4, probability is this, right. This is what we obtained using formula. Let us take the same example. Let us say mean arrival rate is 2.5, and what is the probability that 8 patients will arrive at weekend evenings. So, x is equal to 8. So, what would be the answer? Just look at this column, 2.5 and 8 is this, right. So, this is the probability, it is 0.0031. Similarly, you can find out answer to any question for which mu is known and x is known. Now, this is how the answer to that question would look like if you draw probabilities. So, the probability of 4 patients arriving on weekend is 0.16, right. This is 0.16, is not it. Probability of 0 patient arriving, it is 0.05, 10 patient arriving is it is very near to 0, right. So, there is a pattern over here. What is the pattern? That the probability is first increases, right. It reaches to a maximum value and then starts decreasing. So, when you keep the mean constant and if you change the x, if you increase x, then this is the pattern. So, there is a relationship between how the pattern changes with mu and x. Let us say if you keep the x constant and change the mu, what will happen? Let us look at the table. If you keep the x value constant, let us say 4, and if you change mu, let us say initially it is 2.1. So, this is probability. When you increase mu 2.2, this is 0.10. So, probability has gone up, right. It has again gone up, right, it is going up. So, in this case when you keep the x constant and change the mu or increase the mu, the probabilities also increases. Okay. So, how this the distribution would look like? So, this is your x value, let us say which is constant 4, and the mu, when mu changes then the probability will also change, right. You will get a distribution like this. Okay. Let us look at next slide. So, one of the properties of Poisson distribution is that mean and variance are same. So, what would be the answer to the Mercy Hospital question which we have just solved? What was the mean there? Mean was 3, x was 4, right. So, mean is 3 and variance is also 3, right. So, this is the answer, right. Variance for number of arrivals during 30 minutes period is 3, which is equal to mean as well. Now, we have seen Poisson distribution and binomial distribution, but binomial distribution has got very tedious calculation. You need to calculate a lot. You can approximate Poisson distribution of binomial distribution. So, instead of using binomial distribution, you can use Poisson distribution to solve a question, but there are certain conditions to be fulfilled. This can happen only if n is very large value. Large means either 20 or more than 20, and p is small value, either equal to or less than 0.05. If these two conditions meet, then only you can approximate Poisson distribution for binomial distribution. So, we know that in Poisson distribution you have got mean, and what is the mean of binomial distribution? What is the mean? Mean is it is NP, right. So, if these two conditions are fulfilled, then we can replace this is mean of Poisson distribution lambda, right. So, we can replace lambda by NP if we meet these two conditions, right. So, this is what I have written over here. So, we can substitute mean for binomial distribution is NP in place of mean of Poisson distribution, that is lambda. Let us take an example. In a hospital there are 20 dialysis machines, and at a given point of time or on a given day, the probability that the machine will not work is 0.02. Probability that one of the machines will not work properly is 0.02. What is the probability of 3 machines malfunctioning on a day? So, this information is known to us on the basis of past data. So, what is the probability of 3 machines malfunctioning on a day? So, if you have, let us say, let us look at this. So, we know that Poisson distribution is this, and we know the binomial distribution is this. So, what is the question? The probability that there would be 3 machines not functioning on a given day. So, mu is equal to this NP, right. So, we have put NP instead of mu, right. So, this is N is 20 and P is 0.02, this P, right, to the power x, right, NP to the power x, x is equal to 3 multiplied by e to the power minus mu, and what is mu? In fact, this is mu, right, NP is mu. Okay. Now, the answer here is 0.0071. Now, the same or similar answer can be obtained using binomial distribution. In the absence of Poisson distribution, we would have used binomial distribution. And what is binomial distribution? F of x factorial n divided by factorial x into factorial n minus x, p to the power x and q to the power, this is nothing but q, right, q to the power n minus x. So, answer here is 0.0065, just see almost same answers, right. So, what I am trying to say is that you can use Poisson distribution instead of binomial distribution to avoid its tedious calculation if two conditions are met, and those conditions are what? The n has to be equal to or greater than 20 and p has to be less than or equal to 0.05. Let us look at couple of examples. So, for a given binomial distribution n is equal to 30, p is equal to 0.04, use Poisson distribution to find the answer, right. Since this is a case where n is large, p is small, we can approximate binomial distribution as Poisson distribution. So, what is the probability of success? 25, 3 and 5, right. So, this is n p, lambda is equal to what? N and p, right. So, this is 30 into 0.04, this becomes 1.2. So, e to the power lambda. So, either you call it lambda or mu, one and the same thing. Okay. So, answer to the first part is 0, right. So, the probability that there would be x r value is equal to 25 is 0, r is 3 is equal to 0.08 and r equal to 5 is 0.0062. So, this is how you can approximate Poisson distribution for binomial distribution. Let us look at one more distribution. This is hypergeometric distribution. Now, this is somewhat similar to binomial distribution with few changes. So, statisticians often use the hypergeometric distribution to complement the analysis that can be made using binomial distribution. So, we know that in binomial distribution we perform our experiments with replacement. Okay. So, always we perform experiment with replacement. So, let us say if there are 4 chits in a box, we will take out one chit, and next time when we perform the experiment we will keep the chit again and again we will take out one more chip or 2 chips, whatever is the question. So, here the experiment is or the trials are done with replacement in binomial distribution, but in case of hypergeometric distribution they are done without replacement. So, the trials are done without replacement. So, this is the basic difference between these two. There are certain characteristics of hypergeometric distribution. So, of course, it is a discrete distribution. Each outcome consists of either success or failure. It is similar to what we have seen in case of binomial distribution. Sampling is done, this is the only difference, this is one of the differences, right. The population is finite and known. The number of success in probability is known, and the probability of success changes from trial to trial, while in previous case, in case of binomial distribution, this remains fixed. Okay. So, these are a couple of characteristics of hypergeometric distribution. So, if you look at hypergeometric distribution, the probability function is given by its R C x n minus r c n minus x and capital N c n. So, small n is number of trials, capital N is the population, total population, number of elements in population, r is number of elements in the population labeled as success. So, this you always try to find out r. Okay. And for this probability function is valid for x is equal to x is ranging between 0 and r. Now, if you look at this RCX is nothing but the number of ways x successes can be selected from total r successes. So, there are total r successes and we can find out number of ways of x successes. Similarly, this portion of the formula deals with the n minus r failures out of n minus x total failures, right. So, the number of ways n minus x failures can be selected out of n minus r failures. Similarly, number of ways of sample size n which can be selected out of n. So, all these three are you need not remember these points, right. So, we want to select x successes out of r, we want to select n minus x failures out of n minus r, we want to select small n sample size out of capital N, right. Let us look at an example on hypergeometric distribution. Bob Navarrete has removed 2 dead batteries from a flashlight. So, this is flashlight and he inadvertently mingled with the 2 good batteries he intended as replacement. The 4 batteries look identical. So, you can just think of these are 4 batteries, they look alike. So, 2 of them are dead batteries and 2 of them are good batteries. Now, Bob randomly selects 2 of the 4 batteries. What is the probability that he selects 2 good batteries, right? So, that is the question. Now, you can solve this question. So, if you look at how many total batteries, n is equal to 4, right, is not it? So, you need to find out what is R, what is X, is not it? What is n minus R and n minus X, is not it? So, let us look at this. So, X is number of good batteries, right. R is number of good batteries in total. So, we have to select this RCX, right. So, this is number of good batteries selected, number of good batteries in total. Of course, small n number of batteries selected. So, the Bob has selected 2 batteries out of 4 batteries. So, if you put all these values in this formula, you will get answer equal to 0.167. So, this is how you can solve a question like this. Now, the mean of hypergeometric distribution. So, we have seen mean of Poisson distribution, mean of binomial distribution. So, for binomial distribution, what was the mean? NP, right. For Poisson distribution, what was the mean? Mean and variance were same for Poisson distribution. For hypergeometric distribution, mean is this, right. It is RCN, right, into n. Similarly, variance. So, if I ask you to calculate standard deviation, what would you do? You just standard deviation would be this value, is not it? Just take positive square root of it, right. So, for the question which we have taken up, wherein there were total 4 batteries, 2 were dead batteries, 2 were good batteries, is not it. So, mean is 1, this n and RCN, right. This is variance, it is 0.33. Now, there are a couple of features of geometric distribution. Now, if the population size is large, then this term in the probability function formula approaches 1, and in that case the mean is this and variance is this. Otherwise, what was the formula for mean? This was mean and this was variance, right. So, this formula, these two formulae change when you change or when your population size is large, then this term becomes 1, right, and the formula changes to this for mean and variance. So far we discussed about discrete probability distributions. Let us look at continuous probability distribution. Now, there are several continuous probability distributions, we will see few of them. So, what is continuous probability distribution? Continuous random variable can assume any value in interval on the real line or in collection of intervals. So, it is not possible to talk about the probability of the random variable assuming a particular variable value, but instead we talk about the probability of the random variable assuming a value within given range or interval. So, we do not talk about the probability of random variable assuming a particular value, but the probability of random variable assuming a value within given interval, right. So, the probability of random variable assuming a value within some interval, let us say x1 to x2, is defined as the area under the graph of the probability density function between x1 and x2. So, these are different continuous probability distributions. You got uniform probability distribution. So, what is the probability between x1 and x2 is the area under the graph of the probability density function between x1 and x2, right. Similarly, for normal distribution, this is the area under curve and this for exponential distribution. So, we will see one by one. First of all, we will look at uniform distribution. A random variable is uniformly distributed whenever the probability is proportional to the interval's length. So, the uniform probability density function is f of x, it is 1 upon b minus a for x ranging between a to b, otherwise 0. So, if x is not between a and b, then f of x is 0. So, a is smallest value of the variable which the variable can take and is the maximum value. Let us work out couple of examples. So, the mean of uniform probability distribution is a plus b by 2 and variance is b minus a whole square divided by 12. So, this is variance. If I ask you to calculate standard deviation, then it becomes b minus a whole square like this, or you can simply remove this and this is under root of 12, is not it. So, this becomes standard deviation. So, mean is this and standard deviation is this, right. Let us take an example, Slater's buffet example. So, Slater customers are charged for amount of salad they take. Sampling suggests that the amount of salad taken is uniformly distributed between 5 ounces to 15 ounces. Find out mean and standard deviation for this question. So, mean is, so a is 5, b is 15, mean is a plus b by 2. So, mean is right. So, this is mean is 10. Of course, standard deviation would be b minus a whole square divided by under root of 12, right. That would be standard deviation. So, f of x is 1 upon b minus a, right. So, this becomes 10, 15 minus 5 is 10. So, x is salad plate filling weight, okay, in terms of ounce. So, mean is 10, this is how we have already calculated. Let us look at variance. So, b minus a whole square divided by 12 is the variance, it is 8.33, right. And I have already talked about variance would be what, this variance, and standard deviation would be under root of 8.33, right. This just skip this, right. Okay. So, this how you can calculate the mean and variance of uniform probability distribution. So, we will continue with the same example. So, this is f of x is 1 by 10. So, this is that value 1 by 10. The a value is 5, b value is 15 and this is mean 15, right. Now, the question is this. Now, the second part of the question is, the first part was we calculated mean and standard deviation. Now, the second part is what is the probability that a customer will take between 12 to 15 ounces of salad. Now, this is what we have already worked out. We have to find out what is the probability that he will take between 12 to 15 ounces. So, 12 is somewhere here, right, is not it? So, this 12. Okay. So, we have to find out this area and we will multiply that value by 1 by 10, right. So, this 12. Okay. So, probability that a customer will take between 12 to 15 ounces of salad is 0.3, right. So, this is 15 minus 12 is 3 into 1 by 10. So, it becomes 0.33. Okay. So, if I ask you what is the probability that a customer will take between, let us say 8 to 14, what would be the answer? So, we know this is 1 by 10, is not it, and between 8 to 14 it means 6. So, this is multiplied by 6. So, it is 0.6, is not it. So, this is very simple question. So, if you are given A and B values, you can easily calculate the probabilities for any given range. Let me put the same question in different way. Let us say you are waiting at the airport and for a particular flight you have observed that the mean the waiting time ranges from 20 minutes to 30 minutes, right. Now, the question is, what is the probability that a passenger has to wait between, let us say 25 to 30 hours. So, how would you solve this question? So, this is very simple. You have got 20, this 30. So, mean would be 25, is not it, and this is 1 by 10 again, is not it, b 1 upon b minus a, right. So, 1 by 10. So, probability between 25 and 30 minutes would be 5. So, 1 by 10 into 5. So, this becomes 1 by 2, this is 0.5, right. So, this how you can apply this formula to different situations. Now, let us look at the most widely used continuous distribution. So, before going for normal probability distribution, let me summarize what we did so far. We have seen discrete distributions like binomial, Poisson, hypergeometric, and we have seen continuous distribution, that is uniform probability continuous distribution. Before taking normal probability distribution, you should have thorough knowledge of discrete distributions, and as far as normal distribution is concerned, it can be applied to variety of situations. So, we will discuss about normal probability distribution in next session. Thank you.